is review for the periodic table test and Regents chemistry. So, first thing you need to know is stuff about the periodic table, how it's arranged, etc. So, here is my fantastic drawing of what it sort of looks like. Okay? Now, you need to know that it's arranged by atomic number or protons. Okay, remember that atomic number and protons are essentially the same thing. Okay, it's organized by groups and periods. Periods go across like this. Okay, and I don't think, yes, it is. Good. Periods go across. So these are periods. And groups go down. Okay, so groups are the columns. Okay, groups are columns, periods are rows. Okay, so that's kind of how the periodic table's arranged. Now, elements in the same group mean they have the same valence electrons, which means they have the same properties. That's why they're arranged the way they are. Okay? Same properties, same group. So if you have something here and here, it's going to be more similar than if you had something here and here. Okay? Groups are families, so same group, same properties. Now, you need to know what each group is. Most of the groups are. So this group right here is your alkali metals. The group next to it are your alkaline earth metals. And they're both so reactive that you don't find them unreacted naturally on Earth. Okay? They're both very reactive and they're both metals. Your metalloids are on and above the staircase. Okay, so they're here, 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 etc. Except for aluminum. Aluminum is not a metalloid. Think about aluminum foil. That's definitely a metal. Okay? And your metals are this way. And your nonmetals are over here. There's way more metals on the periodic table than there are nonmetals. Okay? The middle columns 3 through 11 here, those are your transition elements. The big thing you need to know about transition elements is they have color. Okay? When they are in solution, they form colored ions. Then you've got group 17. These are your halogens. They're the halos next to the gods of chemistry. Over here, your noble gases. Okay? Noble gases. Noble gases do not react because they have a full valence shell. Okay? They are inert. They are the gods of chemistry. They are perfect and happy and stable because they have full valence shells. Those are the groups that you need to know. You need to know where to find metals, know where to find nonmetals. You need to know periods are the same as the number of shells or occupied energy levels. Number of shells. So if it's in period 3, it has 3 shells. If it's in period 7, it has 7 shells. Okay, that's important to know. And that's kind of the arrangement of the periodic table and why it has the shape that it does. All right, ionic radius. So you need to talk about ions. So here's an atom. An atom can lose an electron or gain an electron. And you have a packet that you did on Tuesday after the snow day that explains this. If an atom loses an electron, E minus is an electron, it loses a negative, so it becomes positive. And this is a cation, not a cation, but a cation. Okay? If it gains an electron, it gains a negative, and it becomes negatively charged. Okay? And that is an anion, not an onion, but an anion. Okay? So an atom is neutral. That means it has no charge. That means equal electrons and protons. Okay? If it loses an electron, it forms a cation. If it gains an electron, it forms an anion. Okay? Cations are positively charged, much like the T in cat is a plus sign. Cations are positively charged, and anions are negatively charged. Now, compare to the parent atom. The parent atom is this neutral atom up here. If you lose an electron, you get smaller. Okay? Less electrons around the table, They can pull in tighter, they can become smaller. Anions gain electrons. More electrons at the table, you need a bigger table. Anions actually get bigger. Remember, electrons are all negative and they repel each other. Finally, who forms cations? Metals. You can look at their oxidation states. If it's a positive oxidation state, it's a cation. Okay? Non-metals tend to form anions. And these are your negative oxidation states. Okay? That's what you need to know about ions. Be comfortable if I give you something like Fe2 plus, and I say, how many electrons are in that? You need to be able to tell me. Look up Fe. Its atomic number is 26. Okay? Its overall charge is +2. That means it's a cation. It did not gain electrons. That's an anion. It lost electrons. So the difference has got to be 2. So it lost 2 electrons, so it has 24 electrons. Okay? That's how you would do that. It's like that table in that packet that we did. Okay. Trends on the periodic table. I could draw another beautiful one. Maybe I will do that over here. Okay. Here is a terrible periodic table, but you get the idea. There's helium and there's hydrogen. Okay. So, beautiful. So, what we have here are different trends. There are 4 big trends that you need to know as you go across and down a periodic table. When they say across, they mean across a period, within the same period. So period 2 is a really good example, okay? So when they say across a period, use period 2 as your example. When they say down a group, they mean as you go from the top down the group, okay? So maybe use group 1 or group 17. Those are both really good examples as well. Okay. You need to know the definitions of most of these, and some of them are pretty easy. Radius is just the size of the atom, okay? Metallic character, which is really the same as metallic activity, or non-metallic activity and non-metallic character, okay? Metallic character is the ability to lose electrons, okay? Whereas non-metallic character and activity is the ability to gain electrons. Okay, those are the only things you can gain or lose. Ionization energy is how hard the atom holds onto its own electrons. So a high ionization energy means it does not easily lose electrons. So it's not really a measure of how easy it is to remove an electron, because a low ionization energy loses an electron easily. So this is a measure of how much energy it takes to remove one electron. Let's say that. That's a G, to remove electrons. Okay, how much energy does it take to remove electrons? Electronegativity is the tendency to gain electrons, so it's kind of the opposite. But not really, because the trends here are the same, okay? Ionization energy is how much energy it needs to remove an electron. So if it takes a lot of energy to remove an electron, it's probably going to have a tendency to gain them relatively easily, okay? If it does not have a tendency to gain electrons, then it might have a lower ionization energy, because it won't take much energy to remove one either, okay? So let's see if I can erase this red stuff and we can start talking about trends. All right. You'll know that rad is radius, and we'll go with that. Okay. So let's start with electronegativity. What's really helpful to know is that fluorine right here has the highest electronegativity. Fluorine's the biggest bully on the periodic table, and fluorine can take an electron from almost anyone. Okay, so this is your highest electronegativity. Your lowest electronegativity is down here at francium. Okay, francium is generally your lowest electronegativity. Francium is a huge atom. He has no desire to gain electrons because he has one electron to lose, and that's it. And then he's happy. He's got a full valence shell. Okay, so the francium is your low electronegativity. So across, electronegativity goes up, and as you go down, electronegativity goes down. Okay, down a group, you lose electronegativity. Across a period, electronegativity goes up. So your highest is fluorine, and your lowest is francium. Don't have to memorize that. Look it up in Table S. But it's helpful to keep francium and fluorine in mind because those are some really good examples that you can go back and check. Okay? Ionization energy has the same trends as electronegativity. Okay? Ionization energy and electronegativity have the same trends. However, your highest ionization energy is going to be up here in helium, and your lowest is still here at francium. Okay? Why does helium have the highest ionization energy and not fluorine? Because helium doesn't have an electronegativity. Okay? So when we look at electronegativities, we're really looking at this part of the periodic table. Noble gases have no electronegativity. Okay? They have no electronegativity because they have no tendency to gain electrons because they are already perfect. They already have a valence shell of 8. Okay? They already have a full valence shell, so they have no desire to gain electrons, which is why they have such a high electronegativity. That's why helium is your highest, okay? Because it has its perfect valence shell. It has no shields. We'll talk a little bit about shielding. It has no shields in the way, and that nucleus can hold on to those 2 electrons with a ton of power. Okay, so that's why helium has the highest. The trend is the same though, okay? As you go across a group, ionization energy goes up, and as you go down a group, ionization energy goes down. Atomic radius is the opposite. Let's use a different color, okay? Atomic radius is the opposite. Atomic radius, as you go across a group, it goes down, and as you go down a group, it goes up, okay? So atomic radius, as your radius goes up, ionization energy and electronegativity go down. Again, radius you can look up in table S. So francium here is going to be your biggest. Okay? And over here, your lowest, your smallest is going to be up here, like fluorine, helium. Okay? Helium is going to be, that's right, small. So as you go across a group, the radius actually decreases. That's really important to note, okay? Because that's kind of counterintuitive. You kind of think, oh, I've got more electrons, it should be bigger. But more electrons, but with a stronger nucleus, okay? Your nucleus gets stronger, so it pulls the electrons in tighter, so it actually gets smaller. So radius decreases across a period because of a stronger nucleus. Finally, metallic character and activity. Your most metally metal, your most metallic metal is francium. Guess, let's do this in red, because that's the one we haven't used yet. Francium. Over here, guess what? Francium is kind of the main one for a lot of these. Francium's the most metallic because it most easily loses electrons. Francium loses electrons quite easily. It's so big. It has a low ionization energy, a tiny electronegativity, so it loses electrons easily, and that is metallic character and metallic activity. Your least metallic is going to be fluorine, okay? And as you get further from francium, your metal activity and your metal character is going to decrease, okay? Fluorine has the most non-metallic character. And activity. Again, we're not including the noble gases in this analysis because noble gases have no activity. They do not play in the chemistry game, remember? They do not react. They don't need to. They have a full valence shell. The rest of the elements in the periodic table react because they need to have a full valence shell. Okay, so that's kind of how it works. And that is it. That's most of everything that you need to know. I'd highly suggest going through those review packets, making sure that you know how to read valence electrons. It's the outermost shell, the last number. Know how to figure out how many electrons are in an ion. Um, and remember that transition metals are colored in solution. Otherwise, you should be all set. Good luck.